This lecture is on Taylor and Maclaurin series. We've already discussed Taylor polynomials. We've discussed infinite power series, and now we're combining the two ideas. Basically what we had before in earlier sections, but now we've got a dot, 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 and you see we're going to an infinite number of terms, this being our general term for our Taylor series. Now, as far as forming a specific power series, we can come down here, and if we look at our function sine x, we're doing a Maclaurin series, so therefore c is equal to 0. Here's our general term. We can expand it out. We need to get all of these values at 0, so here's our list of derivatives. This is what we get at 0. With all of these numbers, we can plug into our formula, simplify sufficiently, and we get down to this odd polynomial. It makes sense that it's odd considering sine is an odd function. And if we do the ratio test with this general term, we would see that in fact this series does converge for all real numbers. Another way to think of convergence is explored down here. This idea being that this is our Lagrange remainder for our series, and given the fact that if we use more and more terms, if our remainder were to go to 0, then our approximation would basically then equal our true function value. That's what we're saying here, is we let n go to infinity, so we use higher and higher order polynomial, and if the remainder does go to 0, then our Taylor series does indeed converge to f of x. And so here is an example of that. So rather than using the ratio test, what we do instead is we have our Maclaurin series for sine, given by this set of polynomials with this general one. Our Lagrange remainder is that n plus first derivative at z over n plus 1 factorial times x to the n plus 1. Once again, we let the n plus first derivative at z just equal 1, rather than picking a specific value of z, because we know that this will max out at 1. This expression then is our Lagrange remainder, and as n goes to infinity, that is, we use higher and higher terms, this will go to 0, therefore showing again that the Maclaurin series for sine x does converge to sine x for all x. So here are some guidelines then for finding a Taylor series. We have that general term, of course, given over here, and so we need to find out what f of c, f prime of c is, f double prime of c, and so on. If you can recognize a pattern in the numbers, that's great, because then it's much easier to put in sigma notation. And then we use this sequence developed the way we did Taylor coefficients before we did Taylor polynomials to form our power series, try to find the interval of convergence for the power series, and then within that interval determine whether or not the series converges to x, and so that's when we look at remainders. Now, as far as finding these things, despite the fact that you've got this particular procedure, these guidelines, already we see that there are better ways to do these often, so we're already contradicting ourselves. We want to find the Maclaurin series for f of x equals sine x squared. Well, fine, let's find a bunch of derivatives for it. First derivative is not too much of a problem, but by the time you get to the second one, you've already got product rule, and then it gets much worse from there. And so a much better way to go about it is we take our series for sine x and simply plug in an x squared wherever we see an x to get the sign for sine x squared. So here's our new series for sine x squared. And so if we have a basic list of series, we can use that along with substitutions of this manner to get more complicated series. So this is a basic list of some functions. Important ones to know: e to the x, sine x, cosine x. One of these geometric ones, as long as you know sort of one of them, or 1 over 1 minus x to get the others from them, is useful as well. And once we have those, then we can derive from that list. So if we want to find the power series for cosine of rad x, once again, instead of going through all of the differentiation, we take the series for cosine x, but wherever we see an x, we put a rad x, and now we get down to this series here. More examples of finding new series from other ones we already know. First three non-zero terms. So they're not looking for a general term, which is important to note. You'll see for e to the x arctan, well, here's the series for e to the x. Here's arctan with the dot, dot, dots. And clearly we can't do this in general because we would be foiling forever. But if we just take the first few terms and simplify, we can end up getting down here for the first three terms of e to the x arctan. For tan x, we can think of that as sine divided by cosine. And so here's the first few for sine, here's the first few for cosine. If you do long division, you end up getting the first three for tan x. So that's for just getting a few specific non-zero terms. Now for something like this, sine squared x, rather than doing sine times sine, if we just want to get a general power series, here's a clever way to go about it. For sine squared x, we use a power reducing formula and write it as 1 minus cosine 2x over 2, which we can then write as 1/2 minus cosine 2x over 2. Well, we have the series for cosine. Here it is. Memorize that one. To get the series for cosine 2x, simply plug in 2x wherever you see an x. Then you take that series, multiply it by negative 1/2. So we take everything and multiply by negative 1/2. And then finally, we have to add 1/2 to it. And so, in adding 1/2 to it, there's some cancellations, and eventually we get down to this as our series for sine squared x, which will converge for all real numbers. This is an important example in terms of probability studies. E to the negative x squared is a basic bell curve, and finding areas under bell curves is central to finding probabilities. So that means we have to find an integral under e to the negative x squared. So if we want to find the integral from 0 to 1 of e to the negative x squared dx with an error of less than 0.01, well, let's try to do this in terms of series, since we can't just integrate it using the fundamental theorem. So we take our series for e to the x, then wherever we see an x, we put a negative x squared. So here's our series for e to the negative x squared, and then we integrate that series with the power rule. So this is the series for e to the negative x squared. We have our limits from 0 to 1. You plug those numbers in, and you get these 5 terms. Now we want to be within 0.01. This is an alternating series. Because 1 over 216 is less than 0.01, we know that if we just take the first 4 terms, we'll be within our error tolerance. These first 4 terms come out to 0.74, and we're within this as our error term. Another example of that idea, arctan of x over x from 0 to 1/2. So let's start with the arctan series. Here's the arctan series, which again we can derive from a 1 over 1 minus x leading to a 1 over 1 plus x squared and integrating. That was from a previous section, or just take it off a list. Now we have arctan x over x, so we simply divide by x, so this 2 to the n plus 1 becomes x to the 2n plus 1 becomes x to the 2n. We'll integrate that, so power rule. So we add 1 to the exponent, so it goes back to 2n plus 1, but then we divide by it, so this is 2n plus 1 squared. You plug in your limits of integration. Plugging in zeros isn't going to do anything. You plug in the half, we'll end up getting these as our values. So zeros don't give you anything, halves give you all of these, which comes out to 0.4872. And the next term, because it's an alternating series, so we can use alternating series remainder, would be this value, which is less than 0.0001. So if you wanted to approximate this integral to within this error bound, you would need to have then 4 terms, because the fifth is less than that error bound, and your approximation would be 0.4872.